the important laws in physics is the first law of thermodynamics, which can be summarized as stating that the total amount of energy in the universe is constant. This is to say that in this lecture about energy generation, we are not going to discuss how energy is created from scratch. This is not what is meant by energy generation. This is about listing the possible sources of energy existing around us that can be transformed into the type of energy necessary to do our tasks. Let us focus on the task of charging the battery of your phone. This requires a source of electric current. The most direct way to achieve this is by using a photovoltaic cell, known also as a solar panel. It starts with radiation and light of the sun being captured by the cells. Electrons are dislodged in the semiconductors and form an electric current. Also involving the sun, but in an indirect way, is hydroelectric power. The energy from the sun is used to evaporate surface water. Then the vapor and small water droplets form clouds that move over higher ground. Eventually the droplets get too heavy and they change into rain. Some of the rainwater gathers into streams that lead to a reservoir behind a dam. The net result of those transfers of energy so far is a rise of gravitational potential energy for the water compared to oceans and lakes. Next, the water is led down a channel to go past a turbine. Part of the kinetic energy of the water is transferred to the turbine, and the motion of the turbine with the help of powerful magnets induces electric currents. The subject of induced current will be covered later. Other fluid can be used to turn turbines. Moving air, i.e. wind, is an example. The kinetic energy of the wind can be transferred to a turbine, and the turbine can again induce electric currents. Talking about fluids that can move turbines, another example is water vapor. Any source of energy that can be directed to warming water can then lead to induced electric currents by turbines. This can be achieved by the combustion of fossil fuels or biomass like wood. Here, the form of energy at the source is the potential energy stored in chemical bonds. It requires a chemical reaction that leaves the products warmer than the reactants were. The warm products can warm the water. The water turns into steam. The steam moves the turbine. The turbine induces an electrical current. The warming up of the water does not need to be done through contact with products of a chemical reaction. It could also be done with a nuclear reaction. The energy stored in nuclear bonds is much larger than in chemical bonds. The amount of energy released in a nuclear reaction will be discussed later, but essentially, the process of getting an electric current to charge the cell phone has some similarities with the combustion of fossil fuel. The nuclear reaction releases kinetic energy to the products. The energy of the products eventually warm up the water into steam. The kinetic energy of the steam moves the turbine, and the turbine induces an electric current. Other ways to warm up the water into steam involves the increase in temperature as you dig deeper and deeper into the ground, where magma warms up surrounding rocks and underground water. This is geothermal energy. Mirrors can concentrate the sun energy towards water and turn it into steam for a turbine. This is solar thermal energy. Finally, tidal power uses the kinetic energy of the ocean water. This motion is due to the effect of the gravitational force exerted by the moon and the sun on the water. The tidal water moves a turbine, which next induces an electric current. Let us now do a numerical problem involving such a transformation of energy. the case of the hydroelectric power plant. Its input energy comes from the gravitational potential energy of the water that enters the reservoir. So here is our water entering the reservoir, and here is our reservoir behind the dam. The turbine is lower than the water level of the reservoir. Let us set the zero height at the level of the turbine and call the height of the water level of the reservoir as HW. The givens are the height of the water level of the reservoir and the flow rate of the water. We had not set a variable name for such a quantity yet. Let's call it capital R. Notice from the measurement units of R that it is a ratio of mass and time. 1 metric ton is 1,000 kilogram. The last given is the efficiency. Let us recall the relationship between power output and power input. The power input is due to the change in gravitational potential energy. I have added the absolute value sign as a reminder that, by definition, power input is positive. And here, since the water entering the reservoir is at a higher height than when it exits at the turbine, the delta Eg would have been negative. We are only interested in the positive amount of energy involved, and since the gravitational potential energy is zero at the end, the energy lost is the gravitational potential energy at the start, mgHw. M here is the mass of the water flowing through the turbine during the time delta t. So the ratio m over delta t is the flow rate, capital R. We are now ready to use the numerical values of the givens and to find the numerical answer to the power output. Here is our final statement. We will now look at the transfer of kinetic energy of the wind to a wind turbine. So here is a wind turbine with 3 blades shown at somewhat of an angle to the plane containing the blades. The tips of the blades travel on a circle of radius r equal to the length of the blade. We are to assume that all the air coming in the cylinder in front of the wind turbine will be interacting with the turbine during the time interval delta t. The length of the cylinder is v delta t, where v is the wind speed. The givens are the length of the blade, which is also the radius of the circle, the speed of the wind, and the density of the air. Here the power input involves the loss of the kinetic energy of the air in the cylinder of air in front of the wind turbine during the time delta t, which can be written this way, where m is the mass of the air in the cylinder. The mass is the density times the volume of the cylinder, capital V. The volume of the cylinder is the length of the cylinder, which is small v delta t, times the area of the circle, pi r square. After simplifying the expression, we get this. It is time to substitute our numerical values, making sure that we change kilometers per hour into meters per second. A calculator can be used to find the final numerical answer, leading to this final statement. Empirical formulas for the electric power output of such turbines depend on the wind speed and the size of the blades, just like for the power input. For a typical turbine, the power output is 0.566 r square v cubed, where r is in meter, the wind speed in meters per second, and the power output in watts. Let us evaluate the efficiency of the wind turbine discussed in the previous example. By definition, the efficiency is the ratio of the power output and the power input. Substituting the empirical formula for the power output and the equation that was derived in the previous example for the power input, we get this. Simplifying the expression leads to this. If we use the numerical value for the air density that was given in the previous example, we can evaluate the efficiency to be 30%. It is summarized in this final statement. When discussing the transfer of energy from the combustion of fossil fuel to the creation of an electric current, one of the steps was the transfer of energy from the contact of the warm products with water to turn the water into steam. This was the first qualitative hint at another type of energy called thermal energy. We need to quantify this type of energy. This will be the subject of the next installment.